Dear learners, welcome to week 6 lecture 3. In this lecture, I shall explain the solution technique and mixed type formulation of static bending of finite shell and free vibration of finite shell under Levy type support conditions. Previously, we have considered this finite shell and following the displacement u1, u2 and u3, and these were the partial differential equations and boundary conditions. And using the concept of displacement based approach, I said explain the static bending of Levy type boundary conditions, finite element, finite shell, cylindrical shell. So, in this previous lecture, lecture 2, I said explain that we can make another new variable, define new variable, so that we can convert it to a first order differential equations. So, by doing so, we get a 10 differential equations, simultaneously first order differential equations, and that is non-homogeneous equation. So, the equations equal to Z derivative comma x is equal to A is a matrix which is a 10 by 10 matrix, and Z is 10 cross 1, and this is also 10. This is a modified loading. So, in this way we got a final governing equation which is having derivative along the x direction. Now, these equations basically these are the set of 10 ordinary differential equations, and the solution can be represented like complete solution will be complementary solution and particular solution. So, considering the complementary solutions, we will consider first that Z comma x is equal to A matrix into Z, this part only. So, we can assume the complementary solution C is any matrix e raised to power of lambda x. So, when we substitute equation 2 into equation 1, then it leads to a eigenvalue equation which is like this. Now, finally, we can write like this. So, it is an eigenvalue problem where lambda is the eigenvalue of a matrix A and C is the eigenvectors of a matrix A. So, if we know the matrix A, we can find out the eigenvalues and eigenvectors, and we can write the complementary solutions. The solution can be written in different ways. The very standard solution, like we used to call it as a Pagano type solutions, where or these solution techniques are given in any higher engineering mathematics books, specifically the book by Kresge. So, in that the solution of a simultaneous first order differential equation is expressed, that if roots are real and distinct, then we can assume a complementary solution like let us say Fi into Hi. Hi is our arbitrary constants, and where Fi is a function of eigenvectors and eigenvalues. So, Fi can be written as for a single one that Fi will be C1 e raised to power of lambda 1 x C11 basically, then C12. So, expression is like this Fi Cmi Cni e raised to power lambda nx. So, lambda 1, lambda 2 and C1 comma 10. So, up to 10 we can write. So, in this way that all complementary solutions can be written at let us say for first, second and third. So, ultimately the solution can be Z, and that it will be a matrix complete F and a vector H, basically arbitrary constant. F is known to us because we know the eigenvalues, we know the eigenvectors, and at any x location we can find out. If roots are real and repeated, in that case the solution will be linearly dependent, and if we say that let us say there are two roots and they are same, so second and third constant will be same and it will be linearly dependent. It is written as x times of C2m. So, in this way the solution can be written. In the third case, if the roots are complex conjugate, generally for structural problem, if we think about a composite shell, the most of the time roots are complex conjugate or real and distinct. So, in that case we can write a solution in this form, because the roots, one root will be, let us say lambda 1 is alpha plus I times of beta, and another root lambda 2 will be alpha minus of I times of beta. So, here alpha and beta remain same, only with the plus and minus sign the root is differentiate. So, if the root is in such that, then we can write a solution ZC is equal to F3 of H4, F3 H4, we have to write like this, sorry, F4 and F5, then it will be H5 and H4, because up to 3 we have taken cases, let us say first for real and distinct, second for real and same, and third is the complex conjugate. So, 4 and 5th root, and where F3 will be e raised to power of alpha x. Alpha is the real part of that root and real part of that eigenvector, and cos of beta x. Beta is the imaginary part of the root and minus of imaginary part of eigenvector and sin beta x, and F4 can be written like this. So, there are number of ways to write the solutions. In Professor Jane Reddy's book, it is written in terms of cos hyperbolic and sin hyperbolic. Here we have written directly in terms of a exponential, and in some other way one can use the state space technique when if we are able to get the exponential of a matrix Ax, then it will be the solution, basically that first order differential equation where A is a matrix. So, there are number of techniques one can find out the solutions. So, I have explained that one of the very standard technique used to find out the solutions or write the solutions. Now, if we say that load is independent of the x coordinate, in that case the particular solutions can be written like this. So, in this way that we can get the solution for a static case, and arbitrary constants Hm can be obtained. So, by satisfying the actual boundary condition x is equal to 0 and x is equal to a, which may be clamped, free, simply supported. So, in this way that displacement based Levy type solution is presented. Now, there is another technique is a mixed formulation. I think already discussed in the previous lecture. Again I am just going to review that mixed formulation technique, in which we take displacement as well as stresses are our primary variable. Basically stress resultants are our primary variable. What is the advantage of choosing mixed formulation over a pure displacement based formulation? That very first advantage is that it is naturally leads to a first order differential equation. In the previous case, for the case of displacement, we have to identify or we have to define a new variable so that we can convert second order differential equation into first order differential equation. But if we choose to a mixed formulation approach, then it naturally leads to converts first order differential equation. The next advantage is that boundary conditions are directly satisfied in terms of a primary variables. For example, if the boundary condition is clamped only, then your displacement base gives, there is no problem that u1 is 0 and u2 is 0 and w is 0 and psi 1 is 0 and psi 2 is 0. But if you say that your that edge is free, in that case it will be nxx, mxx, nx theta, qx and mx theta. These are not our primary variable, our primary variables are these. So, we have to satisfy these stress resultant conditions by through the shell constitutive relations, which is again slightly typical. So, but in a mixed formulation, these stress resultants are primary variables. So, we can directly satisfy the boundary conditions. Now, we have 5 partial differential equations and 10 cell constitutive relations. So, overall we have a 15 equations, but at an x is equal to 0 and x is equal to a, we can prescribe only 5 at an edge. So, maximum we can solve 10 variable at a time. So, we have to choose 10 primary variables in such a way that we can satisfy the boundary conditions. So, the variables which is prescribed over the edge x is equal to 0 and x is equal to a will be considered as a primary variables. The other variables which are not in this are considered as a secondary variables. So, for our case u1 0, u2 0, w0, psi 1 and psi 2, 5 displacement variables and 5 stress resultants. These are nxx, mxx, qx, nx theta and mx theta. These are considered as a primary variables because nx, mxx, qx will be specified at an edge x is equal to 0 and x is equal to a. So, the other secondary variables like n theta theta, m theta theta, q theta, m theta x will be considered as a secondary variables. One very important part of this development that you need not to convert your partial differential equations with 5 into a displacement form. So, going to development phase, let us first decide that panel theta is equal to 0 and alpha is simply supported like previously. So, we have assumed your displacement field like this, u1 is 0 cos n, u2 0 is sin n, w is cos theta, sin 1 is cos n bar theta and psi 2 is sin n bar theta. So, we have assumed like this. So, like our displacement variables, we have another stress resultant like nxx, mxx, nx theta, m theta x, mx theta, m theta x and qx are our primary variables, stress resultants. So, we need to express these also in terms of sin and cosine theta. So, using the concept of cell constitutive relations, we can directly say that nxx as nmxx can be written as cos n bar theta because as w is expressed, then nx theta and theta x can be expressed into sin n bar theta, then qx is expressed as cos n bar theta. Similarly, the other variables n theta theta, m theta theta, q theta and then m theta, okay, already I have written that m theta x and theta x can be represented. So, they were also presented as a cosine n theta and this cos omega t is for time variation, that variation along the time. So, we know this that we have assumed that variation along theta direction is like this and rest is our variable of x. So, now we have only that function of x, wherever derivative theta comes up they can be use that Fourier expansion. So, now we have these 5 governing equations, partial differential equations and these are our boundary conditions. This we have satisfied by taking simply supported at edge theta is equal to 0 and alpha. So, we can see that equation number 1 can be expressed in terms of we will put nxx left hand side, rest of the variable to the right hand side. So, n theta x comma theta. So, maybe that n theta x is our variable we can express, or if that is not our variable then we can express in terms of primary variables, then nx theta comma x, from this equation mx comma x, from this equation m theta comma theta. So, here I would like to say that mx theta is our variable, again nx theta is our variable, this is not our variable. So, n theta x is not our variable. So, we have to similarly m theta x is not our variable, we have to convert using the displacement form. Then qx comma x can be written as q theta comma theta and n theta. So, again here q theta comma theta and n theta will be expressed using the cell constitutive relation. So, ultimately here all x derivative left hand side and theta derivative and other to the right hand side. Similarly, from the nxx, that first equation we can find out these things n theta theta, nx theta and theta x. So, from here we can say that u1 0 comma x and psi 1 comma x will keep left hand side and rest of the variable right hand side. So, minus nxx, and similarly nx theta it will come minus nx theta, then mxx and qxx. The other variables like m theta x and q theta. So, we will substitute these variables there. Here you can directly see that there is a theta derivative, and again there is a theta derivative. So, mx theta comma theta. So, again theta derivative will come. So, along x axis there will be one derivative. So, by doing all mathematical simplification, ultimately we come up a set of governing equations which looks like this. Let us say H is a matrix, basically the coefficient of x primary variables. For example, in the case of here it is a coefficient is 1, here the coefficient is 1, coefficient is 1, but here you can say the coefficient is a11 plus b11 by r, here is a coefficient b11 plus d11 by r. So, in this way there is a matrix H is defined and a matrix K and an inertia matrix I and a load vector Q. Now, we can find out x comma x. It will be H inverse of K, H inverse of I, H inverse of Q. So, H inverse of K is known as M, H inverse of I is known as I bar, and H inverse of Q is known as Q bar. So, these are the modified matrix. Now, this is our first order differential equation with non-homogeneous constant or non-homogeneous first order differential equations where M and I are constant matrix, which is very important. The solution is readily available. So, you know that if we are going to solve a bending case, so our x will be u10, u20 and this 5 and 5 stress resultants. So, for the case of a static solution there will be no dynamic term. This equation is similar like that z comma x equal to a times into z plus q. It is similar to that. So, we can get the solution same way. Only difference is that in this x we have a displacement as well as stress resultant. In the previous case, in the case of z we have only displacement and z1, z2 they are second order derivatives basically. If you are interested to solve a free vibration problem, for the case of free vibration problem, x comma x can be written as, because loading is 0. So, here q bar n is 0. So, equation like this. So, only time derivative we have assumed that cos omega t. So, if we take the double derivative it becomes omega square and cos omega t. So, ultimately m minus omega square I into x. So, we can assume a solution same way, that assuming a solution in a complementary form, x is equal to c into e raised to power of lambda x and then substitute it here. So, it becomes a equation like this. So, again modifying that we can call this matrix, let us say m tilde lambda I. So, which is a eigenvalue problem again. Here the major difference from the static to this case is that in the previous case it was just a known matrix, m tilde was known to you. But now for the dynamic case, omega is the natural frequency or a fundamental frequency of the shell which is not known to us. We do not know what is the natural frequency of the system. So, in this is unknown is there. So, we will proceed. I will explain the basic idea that how to solve such kind of system. So, let us assume that lambda I minus m tilde c raised to power e lambda x is equal to 0. So, this is an eigenvalue problem. So, for that case lambda is the eigenvalues of m tilde and c is the eigenvector of m tilde. Then we can write the solution, that complementary solution will be fi and kim, where ki is our arbitrary constants and fi is our function of eigenvalues and eigenvectors. Then applying the boundary conditions, if you write a solution, ultimately that either you apply a displacement based boundary condition or a stress based boundary condition. You say that right hand side that if it is clamped, then all variables is going to be 0, if it is free then is also going to be 0. So, it leads to this equation. So, this is an homogeneous equation that let us say for example, A in mathematics what you write, A bracket x is equal to 0. In that case, the trivial solution that all xi is 0 and non-trivial solution. If a system is having non-trivial solution only means one a unique solution, then if it is a matrix, then the determinant of that matrix must vanish, usko 0, that should be 0. This is the condition. If we pose this condition, so ultimately it reduces to a characteristic equation. So, equation in basically, though it will be in equation of lambda 8 and something, but ultimately it will be a function of omega, that is going to be 0. So, how do we solve this kind of problem? This kind of problem can be solved. First assume if omega is the solution, let us say omega whatever you have chosen, that omega is the solution. If that is the solution, then this Fi is going to be 0, determinant of that. That is the check basically. So, what we will do that we will first assume a solution. So, this kind of problem, let us say there is the steps that first find out the bracket. I will explain with the help of some mathematics. Let us say f, which is a function of x, is equal to x raised to power 4, 3 raised to power x 3 plus 2 raised to power of x square plus 6x, like that. We are interested to find out the solution of this equation. So, that solution will first find out a and b. That is known as bounds of the solutions. If we know the bounds of the solution, then we can definitely say that a function is having some, let us say, negative value here and or in this zone or maybe here and a positive value here. So, it may go like this. So, it may have some 0 value. So, bounds of that a function. So, what we will do that we will start from any value. Sometimes say we can take a guess or initial. For the present shell case, we will take initial guess from the simply supported case or some just we can start from 0.01. So, let us say you have chosen some value, let us say a, you have started with a and then evaluated the function. Then you have designed some delta h increment and evaluated. So, till you will evaluate, then it will change the sign. So, when it will change the sign, then you will assign that a times n h will be going to be b. The function is changing the sign. For present case, this matrix f is basically is equal to 0. So, what we will do, we will increasing, let us say assuming omega 0 is something 0.01 and then second omega will be omega 1 will be omega 0 plus some delta, some functions, and we are going to evaluate. So, we can change the, we can notice that change in sign. So, whenever there will be change in sign, minus sign will come up, or sometimes we can find out the absolute value. When there will be absolute value, then it will form like this, that this will be our A and this will be our B. That from this function value decreasing, 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 and then start increasing, increasing. So, when it start increasing, that value is taken as B, because we are taking a delta. So, we will miss inside that. So, let us say delta increment. So, if you take the absolute value, so it will be like this, that a minimum value we are interested to find out, that will be the solution of our system. So, we are assuming, and first we will find out the bounds of the solutions A and B. If you know the bounds of the system, then I think 90% problem is solved. Once you know the bound, you know that because your delta is very small, your delta increment is very small, it depends upon you sometimes you say 0.1 or 1 or 0.02 or 0.05. So, your delta increment is very small. So, your 50 or 60% problem is solved. If you know the bounds, in that bound function is continuously varying, there is no discontinuity, then we can say that solution will exist between A and B. Now, we have a different techniques. If it is single variable, obviously for the case of omega it is a single variable, we can apply the bisection technique. There you can say that another guess A plus B divided by 2, average of that, and you can evaluate the function value. So, means you can evaluate that determinant of that matrix and you can check the sign. So, if this C is coming here and this is going down, again means this will be the guess. If it is going up, so you have to take A is your starting point. So, bisection technique is a very standard technique. It is taught in undergraduate engineering mathematics. So, using those concepts, one can find out that again C. So, if you check the sign, if it is negative or positive, then A plus C or B plus C, depending upon the sign you can decide and calculate. So, ultimately you can find out a particular value C for which it will be a solution. But it is a numerical solution, it will not be directly 0. So, definitely it will be having some 10 to the power minus 8, 10 to the power minus 3, whatever you define the accuracy, that 0 level. So, if that comes, that meets to your criteria, then you say that frequency is found. Once this frequency is found, then you can start finding out the second frequency. So, before that you have obtained the frequency. So, how do you obtain that whether this frequency is corresponding to which mode? Bending and other, whether it is a. So, in that case, once you know the frequency, if you go to back, now our aim is to find out ultimately this Ki. By doing this determinant f is equal to 0, we have obtained Fi, determinant f is 0. So, we have obtained omega. Now, omega is known to us. So, if omega is known to us, now we have a Fi matrix in which everything is a number. Previously, it was having omega and k equal to 0. So, from there these k arbitrary constant we can find out using by basically sometimes using the method of least square or using the method of basically inverse pseudo inverse. So, there are some method that least square, pseudo inverse, that these methods are generally used to find out the solution, non-trivial solution of a homogeneous system of equations, linear algebraic equations. So, we can find out this k. So, if you substitute in that value of k, so you can find out the mode shapes. So, once you find out the value of all constants, then you can say C is basically f into that constant k, and that will give you the mode shapes. Ultimately, you multiply with something sin n bar theta or cos n bar theta if it is w, which is a function of x, which is now this thing. So, in this way we have find out, and now depending upon the actual value u1 0, u2 0, w naught, psi 1 and psi 2. We will check that maximum value of these. So, out of these variables only one will be maximum, sometimes two will be maximum, so depending upon the type of modes. So, for the case of bending mode, only w naught is going to be maximum. So, w naught is going to be maximum and others variables is going to be less. So, if you plot those mode shapes, so w will be maximum and others will be 0 basically. The most important part of plotting mode shape is that you will divide basically w naught, जो भी आपका value है. For example, this deflection is coming 1 into 10 power minus 10 mm, जो भी कुछ है in terms of like that. So, you divide with all these things. So, ultimately it becomes 1. So, you find that in most of the cases that the magnitude is showing 1. When you see that a mode shapes of a shell and such that, then magnitude is coming 1. So, because of that we divide non-dimensionalizing again, and then when we divide, when this w is maximum, if u2 is maximum, then you have to divide all the variables with the u2. If u1 is maximum, then you have to divide all the variables with the u1 0. So, in this way we can find out the mode shapes, we can find out the frequencies, and most important part is that for the case of Levy, basically for a particular value of n, let us say n is equal to 1, you can find infinite set of frequencies. N is equal to 1, you will get number of frequencies. So, initially you will get all bending frequencies, because bending frequency is the lowest frequencies. After that you will get stretching frequencies, then you will get the shear, coupling. So, all kind of frequencies you can find out. Next is that after doing this free vibration problem of a Levy support cylindrical shell, then one can apply the similar techniques to solve the problem of a spherical shell, problem of a conical shell, or a problem of a generalized doubly curved shell. So, I have explained with the help of first order differential equation. If you go for a higher order shell theories, there you will have more number of equations, and definitely you will have large number of simultaneous equations to be solved. One more important part I would like to say that we have got this equation x comma xi, let us x comma x is equal to, let us say m into x plus I bar into x double dot and so on. So, even now you cannot, means you need not to go by the technique which I have explained, even directly in the MATLAB you can solve this ordinary differential equation. Even directly you can solve this ordinary differential equation into which is Cosmos or COMSOM, that you have to just provide a matrix M, matrix I bar and matrix QM bar. So, for theoretical point of view, that you have to prepare a matrix M very accurately, matrix I very accurately with proper sign, with every consideration. Once you prepare the matrix M and I, then you can solve by any technique, and these days we have some more techniques. I would like to just explain that recently I have gone through some research articles that cell problems are solved using DQM, differential quadrature method. Then we have FDM, which is old technique, finite difference method. Then SSDQM, state space DQM. Then we have a Fourier transform. Then there is a differential integral transform. And we have one says that using EKM, extended Kantorowicz method, and then we have a technique RIDGE, and the very standard is finite element technique, which is a general purpose finite element method. Generally in all the commercial softwares these are applied, that finite element techniques. So, these are the techniques which is used to solve shell equations. The only issue with that, we have to prepare accurately the matrix M or the matrix I bar or the matrix Q n bar, rest of the part can be taken care. So, in this way we can solve a Levy type cylindrical shell or a arbitrary supported shell using the EKM technique or the Navier type. So, static and free vibration problem is solved. So, in the next lectures, week 7, I shall explain the buckling of cylindrical shell and the 3-dimensional solutions of the cylindrical shells. Like I have developed the 2-dimensional solutions. Similarly, we have a 3-dimensional solutions where we do not assume anything, like we do not take, in the present case we have assumed that our displacements u10, u20 or w0 is varying linearly across the thickness. But in the 3-dimensional case we do not assume this, we directly solve that what will be the variation. So, basically 3-dimensional solutions act as a benchmark solutions, and these 2-dimensional solutions are assessed or compared with the 3-dimensional solutions for accuracy. And because 2-dimensional solutions, obviously these are simple and it can be generalized in for many cases. So, we used to mostly develop the 2-dimensional solutions for the shell. Even the for in the very starting I have explained that for the case of shell thick, for the general application, the radius to thickness is very like 100 or 200. So, in that case our first order or the classical shell theory is applicable, but when we have thick like our composite cells, there are some machine components where the shell is thick compared to its length and width. So, we can use the higher order shell theories, and most important part is that in the first order shell theory and classical shell theory, the concept of shear stress is not taken, but in the case of composites, yes, though it is thin, but still the concept of shear stress comes into the picture because of different material property in each layer. So, for that case we have to go for higher order theories, at least FSDT or TOT or some higher order theories. So, with this I would like to say thank you very much.